In this video, we are going to take a look at finding more information based on sine and cosine. Now, what's going to be handy about this next problem is it's going to actually teach you a little bit about reference angles, and it's going to teach you a little bit about SOHCAHTOA. Primarily the SO and the CA of SOHCAHTOA, because SO, S-O-H, is the relationship of sine to its opposite and hypotenuse side, where the CA of SOHCAHTOA is the relationship of cosine to the adjacent and the hypotenuse of its right triangle. So let's take a look at this from a graphic standpoint. So we're going to need a little bit of work with the Pythagorean theorem and also the information given to us by this problem. So it says, by drawing a picture, if the sine of t is equal to negative 1/7, find the point t the point t is in the fourth quadrant, find the cosine of t. Now what we're going to do is we're going to put a point in the fourth quadrant. Now we're not sure if this is the exact location of that point, but let's, for the sake of orienting our picture, here we have it. Now what we're going to do is draw a reference angle to this point to the x-axis. The reference angles are always drawn to the x-axis, so this would be our angle t. Now t stands for theta, and theta is a Greek symbol that looks like this. A lot of textbooks will use the Greek theta, but this book uses the t for theta. Now the sine's relationship is the opposite over hypotenuse. And so therefore, from angle t, we're going to go to the opposite side, which is going to be a 1, and the hypotenuse side, which is going to be a 7. Now you'll know that there's a negative here. Now which one would get the negative? We're going to put the negative with the y value, because in the fourth quadrant our y value is negative, and our x value is positive. Now we need to find that x value, and we need to find it because we need to figure out the cosine of t. And we need to figure out the cosine of t, which is the adjacent over hypotenuse. So if we find the adjacent side, then we have found everything that we need to solve this problem. So thanks to the Pythagorean theorem, which is a squared plus b squared equals c squared, and we have a right triangle here because we created the reference angle from point t at the end here, created by angle t here, we are going to now allow this to be part of a right triangle. And in doing so, our right triangle is a squared plus b squared equals c squared. And a and b correspond to the two legs, and c corresponds to the hypotenuse. Well, I'm going to change that for my purposes here. Instead of a squared plus b squared equals c squared, I'm going to go x squared plus y squared equals hypotenuse squared. And here I don't know my x squared, but I do know my y. My y is negative 1. And I do know my h. In this case, my h is 7. I do like putting any substitution in parentheses because that way I get the squaring done correctly. So negative 1 squared is going to be just 1. And 7 squared is 49. Subtract 1 from both sides using an inverse operation to figure out my x squared. Sorry, I left the 2 off there for just a moment. So x is equal to 48. Take the square root of both sides. X is equal to plus or minus the square root of 48. Now a couple things to note here. We need to check our relative position of x in the first quadrant. And since x in the first quadrant is positive, we're going to choose the positive symbol. Now, the square root of 48 should be simplified. Now, the square root of 48 can be made as a product of perfect squares, such as the square root of 16 and the not-so-perfect square of square root of 3. So x is going to be equal to the square root of 16 times the square root of 3, which is another way of saying x is equal to 4 square roots of 3. And this is our answer for the adjacent side. It's 4 square roots of 3. So therefore, the cosine in relationship to t, or the cosine of t, is going to be the adjacent side, which is 4 square roots of 3, over the hypotenuse 7. And this is your answer for this problem. The same thing's going to happen for problem 12, except that instead of being in the fourth quadrant, we're going to be in the second quadrant. And the cosine is going to be negative 3/8. So what I'd like you to do is I'd like you to try drawing the picture first and see if you get it right. You know, pause the video right here, try drawing the picture correctly in the second quadrant, and then unpause the video and see if you did it right, or at least think of how you would do it. So the point T is going to be somewhere in the second quadrant, and we're going to make a reference angle to the second quadrant. And there it is. There's our beautiful reference angle, and there's going to be our angle T, or theta, and then here's our point T. Now, we are going to look at the cosine, which is adjacent over hypotenuse. So the adjacent side is going to be 3, and the hypotenuse is going to be 8. But you notice there's a negative there. Well, I probably should just tell you now that the hypotenuse is never going to get the negative. We're going to treat that like a distance, maybe an absolute value of a distance problem here. So the 3 is going to be negative because it is in the x position, and the x position in the second quadrant is negative. So we are using our Pythagorean theorem, x squared plus y squared equals h squared, and x is going to be, in this case, negative 3. Negative 3 squared plus y squared, which we don't know yet. This is our missing side. And we're going to need to find our missing side because the sine is the opposite over hypotenuse. And since it's opposite over hypotenuse, we're going to need to find that opposite side, y. And here we have h squared. So 9 plus y squared equals h squared. And we actually know the h in this case. Oh, I should have substituted it right there. I'll go back and do that. Okay, so the h in this case is 8. So 8 squared is 64. And then we subtract 9 from both sides using our inverse operation to get the y squared by itself. And 64 minus 9 is 55. Take the square root. Y is equal to plus or minus the square root of 55. Since we're in the second quadrant, the y is positive. Please be careful when you're in the third quadrant. You would be choosing the negative in every situation for finding the x or y. So with this in mind, we now know that our y is equal to the square root of 55. And the square root of 55 cannot be divided by a perfect square, like 4, 9, 16, 25, 36, and so on. So this is the answer for y as its most simplified radical. Please don't turn these into decimals, because we're looking for the exact value, and the exact value is this irrational number. In fact, it's the irrational number divided by the hypotenuse, so the square root of 55 divided by 8. That is our answer for problem number 12. So for the final part of this video, we are going to definitely make our life easier on ourselves if we go and use the unit circle from the session 1 video. If you use the circle from the session 1 video, you will have all of these measurements. And in fact, this is kind of, this section here is a reminder of how radicals are multiplied. In the previous section of this video, we showed how to simplify a radical when the square root of 48 could be broken into smaller versions of itself, or at least you could, take out a perfect square. In this situation, we're going to look at multiplying two radicals by each other and some of the properties we get from there. Now, 5 pi over 6 is findable on the unit circle that you've built from the unit circle from the session 1 video, part 3. So that 5 pi over 6 is 1/2. And 2 pi over 3 is square root of 3 over 2. And one of my favorite patterns is multiplying fractions, not a problem. Top times top, which is 1 times square root of 3, which is square root of 3, and bottom times bottom, which is 4. And that's the answer for problem 13. A very straightforward problem that you could easily have found by looking at your unit circle from the session 1 video. But now we're going to get into some more complicated ones that aren't just so obvious. Well, first of all, take a look at this negative radical. This negative 4 pi over 3 is like negative 240 degrees. So if you have to think to yourself, like, okay, if I'm going negative 240 degrees, where would it be going positive? And if you were to look at that going negative, this would be like going beyond 180 degrees, and 180 degrees and another 60 degrees would be taking you right about here. So the positive way to get there, which is counterclockwise, would be 120 degrees, or 360 minus 240. So really this problem is the sine of 120 degrees times the cosine of 90 degrees. And the sine of 120 degrees is the square root of 3 over 2. Again, that's from the unit circle we built. The cosine of 90 degrees is nothing, because that would be the x value at 90 degrees, and the x value at 90 degrees at the point 0, 1 is 0, which you know because you made a chart. So the answer to problem number 14 is 0. For problem 15, we are looking at the sine of pi over 6 times the cosine of negative pi over 3. Now luckily pi over 6 is really easy to find on the unit circle. It's a 30-degree angle, and the y value at the 30-degree angle is 1/2. Now the cosine at negative pi over 3, first of all, a good way to think of it is if you see yourself going clockwise pi over 3, it takes you negative 60 degrees in this direction. So negative 60 degrees in the clockwise direction. Okay? So negative 60 degrees in the clockwise direction is the same as when you subtract that from 360 degrees, you'll see that this is a 300-degree angle here if you went in the counterclockwise direction. So when you look this up on the unit circle, you can look up positive 360 degrees or this location in radians, and I prefer honestly thinking of it as a degree. I think you make fewer mistakes. So this cosine of 300 degrees is going to be equivalent to the x value at that location, and x values are positive, so this is going to be a positive 1/2, and 1/2 times 1/2 is 1/4. Pretty straightforward answer, but this handles the negative easily. So, negative 5 pi over 4, that's negative 225 degrees. Now, you're probably wondering, how did I know it was negative 225 degrees? Well, if I looked on my chart, I would see that the positive 5 pi over 4 is positive 225 degrees. So, what I'll need to do is figure out where the negative 225 degrees is. So, it takes me, beyond 180 degrees to about right here. And this is going to be then a positive counterclockwise rotation of 135 degrees. So this is the sine of 135 degrees. It's really okay to convert from radians to degrees. I really feel that's kind of one of the unwritten rules of this homework assignment, is to convert to degrees. I feel it'll help you. And this 11 pi over 6 is straight up right on your unit circle there, so I'm not going to do the conversion. Because 11 pi over 6 is just another way of saying 330 degrees. Well, I did the conversion, I guess. So this is equal to, the sine at 135 degrees is square root of 2 over 2, because that's one of the 45-degree measurements. And the cosine at that value, since cosine is the x value, is square root of 3 over 2. And it's going to be positive square root of 3 over 2 because the x value is positive in that location. So what we have here is the square root of 2 times square root of 3, which is square root of 6. Can't be further simplified because it can't be divided by any radical that can divide those evenly, like a square root of 4, for example. And this would then be 4. So that's my answer for the problem here. My answer for this problem is square root of 6 over 4. So for our final problem for this video here, we've got the sine of 11 pi over 3. Wow, 11 pi over 3 is quite a massive angle. Now, there's a couple ways you could do this problem. The one way I like to do it is I like to say to myself, okay, this is definitely more than one revolution around the circle. So 11 pi over 3 is greater than 2 pi. And since it's greater than 2 pi, I have to think about what is 2 pi. Well, that would be 6 pi over 3. 6 pi over 3 is the same thing as 2 pi. So this is one spin counterclockwise around the circle. Now, what's left to make up my 11 pi over 3? Well, that would be my 5 pi over 3. And I'm really hoping 5 pi over 3 is on my unit circle. And luckily, it is. 5 pi over 3 is perfectly what I need here. because 5 pi over 3, is going to be 300 degrees. So, this sine of 11 pi over 3 is now converted into a full revolution plus 360 degrees, or sorry, 300 degrees. So we're going to convert that sine of 11 pi over 3 to the sine of 300 degrees. Alright, so we're done with that. Now let's look at this negative 5 pi over 6. Well, the negative 5 pi over 6, we should probably look at the positive 5 pi over 6. And positive 5 pi over 6 is 150 degrees. So this is negative 150 degrees. So if I go negative 150 degrees, which takes me about right here, it takes me 30 degrees away from the 180. So if I was going to go positively to that moment, you know, along my clockwise spin, this takes me to 180 degrees plus the 30, and that 180 degrees plus the 30 is cosine of 210 degrees. So now I just look these up. Alright, so the sine at 300 degrees looks pretty good here because this is my y value, and the y value is negative at that value, so it's negative square root of 3 over 2. And my cosine is the x value at 210 degrees, which is going to be negative. It's going to be negative, and that x value is going to be negative square root of 3 over 2. That's kind of wild. We have essentially this negative square root of 3 times negative square root of 3 is going to be positive square root of 9, or just 3, and we have 3/4 again. Well, that's pretty handy. So this gives me my final answer for the problem, and I feel pretty good because I learned a lot about converting from degrees to radians, looking at radians and degrees that are bigger than 1 revolution, and earlier in the video we did some SOHCAHTOA work which leaned right into the Pythagorean theorem. Well, thanks for learning quite a lot of different concepts here, but you can see in just a small amount of time we really did go over quite a large stretch of working with sine and cosine, or sine and cosine, on the unit circle and off the unit circle for t that happened to be on a point that wasn't with radius 1. Thank you very much for watching.